Okay, welcome to lecture 2. We're going to do a little bit more about limits. Okay, and specifically the first thing I want to talk about is, can you always find a limit of a function as x approaches a value? Okay, I will tell you right now and make it simple. The answer to that question is no. There are some limits that don't exist. You try to find a limit and you find out that there isn't one. Okay, and I can think of three basic ways that can happen. Okay, how a limit can fail to exist, and I want to cover those ways with you. Okay, so let's write here possible ways that the limit of a function as x approaches a value can fail to exist. Okay, so one way is where the two sides disagree. Let me show you what I mean by that. Okay, I'm going to show you a function. I'm not sure if you've heard of this function before. This is called the Signum function. It looks like this. I'll write it down over here for you. So we abbreviate it by SGN. Okay, SGN of x, and here's what it equals. It basically is a function that just picks out whether the number you're plugging in is positive, negative, or 0. Okay, if you plug in a positive number, you will get out 1. That's if x is positive. Okay, if you plug in a negative number, you get out -1. That's if x is negative. What have I left out? I've left out 0. 0 is neither positive nor negative. If you plug 0 into this function, it returns 0. Okay, so this is kind of like, whoops, I didn't mean to do that. So this is kind of like the function that says the number you've plugged in is positive, negative, or neither. Okay, where if the function tells you the number 1, then that means the number was positive. If the function tells you the number -1, that means the number was negative. If the function tells you the number 0, then that means the number was neither positive nor negative. And this is called the Signum function. Okay? Because that's what it's doing, is it's telling you about the sign of the number, positive, negative, or neither. And in fact, a lot of people call it that. They call it the sign function, but you can guess right away why that's a very dangerous name, right? Because if I just said to you verbally, what's the sign of pi? I might be thinking sign like SGN, in which case the answer would be 1. You might be thinking sign like SIN, in which case the answer would be 0. So that's why we have this name Signum, okay, instead of just sine function. But a lot of people do call it the sine function. But if you do, you should say sine, S-I-G-N, not S-I-N-E. Okay? All right, so anyways, let's graph that. If you graph it, it's going to look like this. Okay, so let me ask you a question. Does the signum of 0 exist? Yes, it does. It equals 0, right? Does the limit of the signum of x exist as x approaches 0? The limit of the signum, of x as x approaches 0. What about that? Look at what happens. As x is approaching 0 from the left, the function is approaching what value? That value right there. That's not a point on the graph. That's why I didn't fill it in with blue. But it is the value that the graph is approaching, right? Now, if x is approaching 0 from the right, then the function is approaching an entirely different value. So you have to ask your question. You have to ask this question: what's the answer? Is the answer 1 or is the answer -1? Which one is it? Or is it both? That's a perfectly good question. Is the limit both of those? Well, you have to remember what limit means. Okay, you're asking, do the y values approach a number as the x values are approaching a? And in this case, a is 0. Okay, so does the signum of x approach a number as x approaches 0? Did you hear what article I used? I used the article a. I said, does it approach a number? That's a singular word, isn't it? So in other words, I'm asking, is there a singular number that the sign of x approaches as x approaches 0? Okay, if it's trying to approach two different numbers, a different number from each side, then that means it is not trying to approach a single number. And so the answer to the question, does the sign of x approach a number as x approaches 0? The answer to the question is no. It doesn't approach a number. It's trying to approach two different numbers. And so that limit does not exist. There is no... Oh, hang on one second. I'm sorry to pause here, but I believe I ran off the side of the screen earlier. And so let me shrink this down a little bit so you can see that. Okay. I hope it's not necessary to restart the whole video now that we're 10 minutes in. Okay. So now you should be able to see the whole thing. Okay, so where did I leave off? The signum of x does not approach a single value as x approaches 0. So you say the limit of the signum of x as x approaches 0 doesn't exist. In other words, there is no limit of the signum of x as x approaches 0. Okay? Now we can abbreviate doesn't exist with DNE. That's fine. I'll just show you something. I'm not going to mark anybody wrong if you do this, but it's just a little pet peeve of mine. See, we can write the limit of this function as x approaches 0. You can write dne. I'm perfectly fine with that. Here's something that just kind of bugs me a little bit, is people usually don't do that. They do this. They write equals dne, because here's the reason why. As soon as they start the problem, they write this. And then they wait to figure out the answer, and they're going to fill in the answer. And then when they find out that the limit doesn't exist, they write dne here. I'm not going to mark you wrong if you do that, but grammatically speaking, that doesn't make sense. When you write dne, you should erase the equal sign. Okay? Because otherwise it says the limit of the signum of x as x approaches 0 equals does not exist. And that just is grammatically incorrect. It is a very awkward sentence. Okay? And I know this is math, not grammar, but we should still strive to be grammatically correct in our mathematics. Okay? So that's one way that a limit might fail to exist. It's trying. I'm erasing this extra stuff. I'll put it back here, the original graph. It's trying to have a limit from each side individually, but the two sides can't agree with each other. Okay? Now, you could ask this question, and it would be a very good question. You might ask, well, do we call it something when there's a limit from one side, but a different limit from the other side? Do we call that something, or do we just say that that's nothing? And we do call those things something. They're called one-sided limits, but we're going to cover those later, okay? Right now we're doing limit, not one-sided limit, okay? If the two sides don't agree with each other, then there isn't a limit at that point. Okay, there are limits of this function elsewhere. Like if somebody asked, here, let me show you. Somebody said, what's the limit as x approaches 2? Well, 2 is right around here, right? And as x approaches 2, what value is the Signum function approaching? It's approaching the value 1. So there is a limit of the Signum function as x approaches 1. As x approaches 2. Okay, there's just not a limit as x approaches 0. Okay? All right. What's another way that a limit might fail to exist? Here's sort of an extreme example where the function just can't make up its mind. I'm going to write it like this. Function tries to be everywhere at once. Let me show you an example of something like that. We're going to look at the function, the sine of 1 over x. And we're going to look at what happens when x approaches 0. Okay? Sine of 1 over x. Here's what the function looks like. Give me 1 second. I want to make sure I get this correct. Okay. So it's coming along, and sorry, that keeps shifting. It's coming along and it's behaving fairly well. And it goes up a little bit here, and then it starts going down. Okay, and from the other side, it looks very similar, except it's coming along here, it goes up, it goes down a little, and then starts going up. But everything goes crazy as you get closer and closer to zero. This starts oscillating faster and faster from both sides. And what you get when you get towards the middle is that it oscillates back and forth so quickly that you can't even see the different oscillations anymore. It just looks like this, basically. Okay? And what's happening there is, as x approaches 0, the function is oscillating so quickly between -1 and 1 that you cannot say that there is a single point, a single value that this function is approaching as x approaches 0. I always tell students here, I always say, as x approaches 0, this function is trying to approach all of the numbers between -1 and 1. Okay? So I would say the limit of the sine of 1 over x as x approaches 0 does not exist. Okay? So in that first example, we saw a function that was, I'm just speaking here in common terms when I say that function is trying to approach two different values. Okay, here you have an extreme example where this function is trying to approach many, many different values. In fact, infinitely many values. Because how many numbers are there between -1 and 1? There's infinitely many numbers. Right? Okay. Let's look at this third possibility. The function goes off to infinity. And that could be a positive infinity or a negative infinity. Let's look at the function 1 over x. How about that? Okay, 1 over x is the function we're going to look at. You've seen this before, I imagine. If you graph it, oops, I wanted to make that blue. It looks like this. Okay, and I could say, what's the limit of 1 over x as x approaches 3, right? And the answer would be, well, think about it, it would be 1/3. Not because 1 over 3 is a third, but because 1 over x approaches 1/3 as x approaches 3. Okay, remember, I always want you to remember that. I'm going to scroll for a second here. I just want you to remember that. This does not mean the same thing as this. Sometimes they come out to equal the same, but they don't mean the same. Okay? So here's an example where the limit of 1 over x as x approaches 3 happens to equal 1 over 3. Okay? But that's not because when I plug in 3 I get 1 over 3. It's because as x approaches 3, 1 over x approaches 1/3. Okay? Alright, so let's get back to that. All right, but now let's look at the limit of 1 over x as x approaches 0. And it's a good point if you were to say, oh, I see what's happening. This is just like the first example. The two sides disagree. That is correct. They do. They do disagree. But even if they did agree, there's still another problem. What if we did, I'm not going to erase that, but let me write a second one. Let's write 1 over the absolute value of x. Well, that's a lot bigger than we needed it. So let's put here 1 over the absolute value of x. That one looks like this. So what if I said the limit of 1 over the absolute value of x as x approaches 0? You might say, oh, now they agree with each other. And so now there is going to be a limit. Okay? You might say that. But listen again to what a limit means. It means, is there a number that the function is approaching as x approaches 0? Okay? Now, if I forced you to tell me something that this function is approaching, what's the only thing you could say? You could say it's approaching infinity, right? So let me write that. Let me write equals infinity. Okay? So you're saying then that the function is approaching the number infinity as x approaches 0. Okay. That's right and it's wrong. Okay? Strictly speaking, the sentence I said is wrong. I'm going to repeat the sentence and see if you can find the error in the sentence. I said, the function is approaching the number infinity as x approaches 0. So what's wrong in that sentence is I said the number infinity. Infinity is not a number. Okay? So if the function's approaching infinity, it's not approaching a number. And so technically that means there's not a limit. Okay? So technically, that doesn't exist. Okay? Technically. But it's still good to point out what information you can. And it's worthwhile pointing out here that the function is, we call it approaching infinity. Technically, it's impossible to approach infinity because no matter how close you get, you're always infinitely far away. But that's still what we call it. We call it approaching infinity. Okay? And that's what's happening here, and that's why the limit doesn't exist. But it's still nice to indicate that fact. So we still write equals infinity. We write that with our pencil. Okay? But it's very important for you to understand infinity is not a number. So if the limit is infinity, then that means there's not a limit. I know that sounds like a self-contradictory statement, but don't let yourself get hung up on the semantics. Okay? Having a limit that is infinity is one type of a limit that doesn't exist, because infinity does not exist in the real numbers. You can't point to a real number to me and say, there it is, there's infinity. I defy you to try to do that. You won't be able to, because there is no real number called infinity. Okay? So if the limit is infinity, then the limit does not exist in the real numbers. And we're doing calculus here with real numbers. Okay? So if the limit's infinity, then the limit doesn't exist in the real numbers. You still write equals infinity, but it's important for you to understand and to know in your mind that that doesn't exist in the real numbers. So if I gave you a question and I did not say what is this limit, but I just said a yes or no question, does that limit exist? The correct answer would be no. Okay, because what I'm asking is, does that limit exist in the real numbers? Okay, and infinity is not in the real numbers. That would be the case for both of these examples. It's just that the first one has an even bigger problem. Besides the fact that the two sides are going to, one's going to positive infinity and the other's going to negative infinity. So that's one problem. And then the other problem besides that is that they're not agreeing anyways. Okay, so that's 3 ways that limits can fail to exist. I'm going to shrink this really small. I'm not expecting you to necessarily try to read it, but I just want you to see a summary here, that those are the 3 ways that a limit can fail to exist. Okay? Okay, one other thing we're going to do today, and that is limits of difference quotients. Okay, let's look at difference quotients. This is something that you learned in pre-calculus. Okay, let me show you what that is. Okay. If we have f of x, the difference quotient is f of x plus h minus f of x over h. Do you remember doing that before? So here's what we're going to do here in calculus now. What's written right there is not calculus, that's just algebra. Now we're going to do some calculus to it. We are going to find the limit of that as h approaches 0, okay, for different functions. And maybe that limit will exist sometimes, and maybe it won't exist other times. Okay? So this is extremely important, all right? Most of this semester is going to hinge upon this part right here. It is extremely important, okay? So we're going to do limits of difference quotients as h approaches 0. Okay, and this is crucially important. So we're just going to do a few examples here. I think that's the best way to do this, is by example. So let's look at the simple linear function f of x equals 4x minus 2. Okay, f of x equals 4x minus 2. All right, I want you to find, well, I'm going to do it with you, find the limit of f of x plus h minus f of x over h as h approaches 0. Okay? Now, let's work it out. These are not difficult. Well, I mean, some of them can be difficult, but the concept is not difficult. It's just a matter of plugging in x plus h to see what you get. Subtract f of x from that. Divide that all by h. and then let h go to 0. You might say, well, wait a minute, is it okay to let the denominator go to 0? You can't have 0 in the denominator. But that's the key. Remember, this is a limit as h is approaching 0. I'm not saying h equals 0. So the limit might be able to be done. It all depends. Just because there's an h in the denominator and h is approaching 0 does not necessarily mean that we're going to get 0 in the denominator. Okay, you'll see in just a second. That might sound impossible, but as soon as we do this one example, you'll see. All right, so let's work this out. So we're going to do the limit as h approaches 0 of, and I'm going to just write this formula here again, and I encourage you to do that because you need to memorize this. And the more often you write f of x plus h minus f of x over h, the better you'll get that memorized. Okay? All right. So what should we have in here in this big fraction? What is f of x plus h? It is certainly not 4x minus 2 plus h. Okay, if you're saying that, then you're not understanding how functions work. Because it doesn't say f of x plus h. It doesn't say to add h to f of x. It says to plug x plus h into the function. So won't I get 4x plus h minus 2? Because that's what the function does. It multiplies the input by 4 and then subtracts 2. So if I'm plugging in x plus h, then the function will multiply that by 4 and then subtract 2, right? Okay, what's next? It says minus f of x. Here's f of x. Okay, and then it says over h. So in order to see what this limit is, I first need to simplify that fraction. So let's do that. And then we'll do the limit as h goes to 0 of, so let's work out what we're going to have. We're going to have 4x plus 4h minus 2 minus 4x plus 2 over h, correct? Now look at all the canceling that's going to happen. 4x and the minus 4x cancel. The minus 2 and the plus 2 cancel. The only thing I'm left with is the limit of 4h over h. And then the h's will cancel. So it is the limit of 4 as h approaches 0. Now that might seem weird to you because there's no h's, is there? But that doesn't change anything. Listen to the question. I'm asking, does the number 4 approach a certain value as h approaches 0? Well, wouldn't it be approaching the number 4? Isn't that what the number 4 approaches? If that doesn't solve it for you, if that's not a good explanation, then let's do this. Look at a graph where this is not the x-axis, but it's the h-axis. And I want to find the limit of the constant function 4. That function looks like this, right? So now as h approaches 0, what is that graph approaching? It's approaching that point right there, isn't it? And what's the y value of that point? It's 4. So that limit is 4. And that's the answer to our question. Okay? The limit of f of x plus h minus f of x over h as h approaches 0 equals 4. And it's no coincidence, by the way, that that is just this number right there. Every time you have a linear function and you do this type of problem, your answer will be that number. But it's not good enough for you to just say, oh, okay, well then every time I get this, I'll just write down that number. No, you have to know why the answer is that number. You have to know how to calculate this, and you have to show me that you know how. So you have to write the problem like we did here. Okay? Let's do one that's a little harder. This time we'll do x squared plus x. The limit of the difference quotient as h approaches 0. And this time I want to use the function x squared plus x. Okay, so we're going to try to find the limit of f of x plus h minus f of x over h as h approaches 0. Okay, so first let's write down what we have, and then we'll try to simplify it. So here's what we have to work with. X plus h squared plus x plus h. That's this right here, isn't it? I plug x plus h into my function, and that's what I would get, correct? Okay, now let's continue. Then there's a minus, and I subtract f of x, which is x squared plus x, and then I divide all of that by h. Now, again, let's say the same thing I said last time. Let me move that over so you can see it. There we go. Same thing I said last time. In order to find that limit, I first need to simplify this fraction. Okay? So let's see what we get here. I'm worried about running off the side of the screen, so I'm going to move over to the left a little. Okay, so we're going to have the limit as h approaches 0. The limit of what? Well, who knows until we just work it out. Oh, why did I put that so high? There we go. Okay, so what's up there? Well, there's an x squared plus 2xh plus h squared. That's this right here, correct? And then there's a plus x plus h, so I'll write plus x plus h. And then there's a minus x squared plus x, so that'll give us minus x squared minus x, and then there's an h on the bottom. Let's see what, if anything, cancels out. This x squared will cancel with that one, and this x will cancel with that one, and that looks like that's all as far as combining like terms on the top. You might see that there's going to be another cancellation in a minute, but right now all I did was combining like terms on the top. Okay, what's left up there? There's still a 2xh, and there's still a plus h squared, and there's still an h. You see how every term that's left up there has an h in it? So in that case, how about if we factor that h out? And let's write it like this: h times 2x plus h plus 1 over h. Can you see why I wanted to do that? Because now I can easily see those two h's canceling. And all I have left here is 2x plus h plus 1, and I want to find the limit as h approaches 0. Well, if you have 2x plus h plus 1 and the h approaches 0, then isn't that going to approach 2x plus 1? There's our answer. Okay? See, it's not hard if you can just do your algebra correctly and cancel out everything that you possibly can. That's all algebra. The calculus doesn't happen until you go from here to here. There's just one small step of calculus at the end. 80% of this problem is simply algebra. Okay? The problem is if you don't know how to do your algebra correctly. Alright, we're going to do one more, and this next one's going to be the hardest one. It's going to be lengthy, but just stick with me. Rewatch the video again if you need to. If you get lost, just rewind a little bit and watch that part again. Okay, the function I want to do is (2x plus 5) over 7x minus 2. Okay, and we want to find the limit of the difference quotient as h approaches 0. Now, mathematically, this is not any different, which means no harder and no easier than the two we just did. It's the same problem as the two we just did. Okay? It's just that because the function is a little bit more complicated than the previous two functions, then this work, the algebra, will just be more complicated. But again, it's just algebra. Okay? So let's start by writing down what we have to work with. Why is that blue? I don't know. Okay. So, what do we have? We have a fraction, right? And what's on the top? First is the function with x plus h plugged in. So that will be 2x plus h plus 5 over, and then I have 7x plus h minus 2. Okay, so that's f of x plus h. And then what comes after that? Minus f of x, which is 2x plus 5 over 7x minus 2. And then what's on the bottom of that big fraction is h. So that's what we're being asked to find right there. In order to find the limit, I need to simplify first to see what I really have here. It's very difficult to look at that and to realize what is really there, because a lot of stuff that you see is going to cancel out, and it's very difficult to see what's going to cancel out the way it's written right now. So we are going to expand that whole thing. And it will seem a bit messy, but we'll be able to tell what's going to cancel then. Okay? So here's what we need to do. Just follow with me. I'll try not to rush. This is nothing more than just algebra. Okay? Alright, what do I have on the top? I have one fraction minus another fraction. Okay, let's start by writing that. One fraction minus another fraction. Okay. What do I need in order to subtract one fraction from another. I need a common denominator, right? Do those two fractions up there have the same denominator? No. One is 7x plus h minus 2, and the other one is 7x minus 2. They aren't the same. How can you get a common denominator? If I give you any two fractions, how can you get a common denominator? You can always multiply the two fractions together, right? If I give you 1/3 and 1/5, isn't a good common denominator 15? And if I give you maybe, what would be another good example? What if I gave you 1/12 and 1/10? Wouldn't a good common denominator be 120? That's not the least common denominator, but it's certainly a common denominator, right? You can always get a common denominator of two fractions by just multiplying the two denominators together. So that's what we're going to do, okay? Our common denominator is going to be 7x plus h minus 2 times 7x minus 2. That's going to be our common denominator. So, what needs to go up here? It should say 2x plus h plus 5 times 7x minus 2. And what should go here? It should say 2x plus 5 times 7x plus h minus 2. You agree with that? It's just doing algebra with fractions. Okay? And now it's just a matter of multiplying that all out to see what we have. Okay? So I'm going to just multiply that stuff all out. And I encourage you to check my work. You might even want to pause the video and multiply it out and see if we get the same thing. Okay? Here's what I ended up with. Right here, that stuff right there, give me a second here to get ready to write this down. Okay, so that part that I highlighted in yellow, I worked that out, and what I got is 14x squared minus 4x plus 14xh minus 4h plus 35x minus 10. So like I said, I encourage you to pause the video and work that out and see if you get the same thing. Okay? Don't just take my word for it. That's not going to be helpful to you. All right. What did I get on the bottom of that? On the bottom, this stuff down here, I multiplied that out and I got 49x squared. Actually, I'm sorry, I'm going to pause for a second. Let's save that for a second. Let's do the top of the next one first. Because isn't it true that when you take one fraction and subtract the other, and the denominators are the same, then you just get one fraction, right? So maybe it's better if we do that. Okay, and then we'll put here minus, and now we'll work this part out. Okay, so what I got there is I'm not sure how much room I'm going to need to fit this in. So what I got is 14x squared plus 35x plus 14xh plus 35h minus 4x minus 10. So you should pause the video and work that out, see if you agree with that. Okay, and now let's do the bottom. Here it's the same denominator, so I only need to write it once. Okay, and I got 49x squared minus 14x plus 49xh minus 14h minus 14x plus 4. All right, let's see what we can cross out. It's actually quite a bit. Okay, here's a 14x squared, and then I am subtracting 14x squared. So those will cancel. Here's a 14x, whoops. Okay, here's a 14xh, and then I am subtracting 14xh, those cancel. All right, what else do we see here? Here's a negative 4x, and then I am subtracting negative 4x, so those cancel. Here's a 35x, darn it. Here's a 35x, and then I am subtracting 35x. And one more. There's a negative 10, and I am subtracting negative 10. Look at all that disappeared. What's left up there? Let's see what's left. There's a negative 4h, and then I am subtracting 35h. So the only thing left out of all of that up there is a negative 39h. Isn't that interesting? How little is left? Just a negative 39h. Okay, but that's over a lot of stuff, right? That's over a 49x squared minus 14x plus 49xh minus 14h minus another 14x plus 4. And then that is all divided by h. Okay, now all along here I've had fractions inside of fractions. I'm going to fix that now. So that big fraction on top is divided by h. So instead of writing over h, let's do it this way. Let's write times 1 over h. And the reason I want to do that is because now it'll be easier for you to see. Look at this. That h is going to cancel with that one. Okay, now we're done with all the algebra. We've got it simplified as much as we can. And here's what we're left with. A negative 39 on top of all this business. if it's okay with you, I'm going to take this negative 14x and this negative 14x, because they're like terms, I'll put them together and write negative 28x. Okay, that's the only like terms I see. And then we have a plus 49xh and a minus 14h and a plus 4. All right, algebra's done. Now we do the calculus. Let h approach 0. What's going to happen? That will disappear, and this will disappear, and we are going to be left with negative 39 over 49x squared minus 28x plus 4. And that's our answer. Okay. Was that hard? Well, I would say no, it wasn't hard at all, but I would say it was tedious. Very tedious, but not difficult. There's a difference, and you're going to have to accept that, you know. Don't call tedious things difficult. Separate in your mind. Be more specific. Call difficult things difficult and call tedious things tedious. Don't convolute them. Okay, because if you start using that language saying that this is hard, then what's going to happen is calculus is going to seem hard to you. We're just getting started. This is just the second lecture. Okay? And if you convince yourself that this kind of stuff that we did right here is hard, then the whole class is going to seem hard to you. Okay? And I think an honest observation would be that this wasn't hard. It was just tedious. Okay? And there's a difference. Okay. The other thing too I'll point out really quickly is all of that tedium that was involved there, it was all stuff that you've covered before in pre-calculus or college algebra, and let's be honest, there's nothing there that wasn't something you had learned in high school, really. It's just subtracting fractions from each other and things like that. Okay? We didn't get to any calculus until the last step, and that was the easiest step of all. All right, it's been almost an hour. We better stop. Have a good afternoon.